So here's the equation for the y motion. Y equals y naught plus v naught yt plus 1/2 ayt squared. We put our values in. Y is 0, y naught is 1.50 meters, v naught y is 10.0 meters per second. Ay is negative 9.8, and then times 1/2 is negative 4.9. So I've already just did that through. Negative 4.90 meters per second squared times t squared. Now, we need to solve this equation for t. How are we going to do that? Well, that is a quadratic equation. So we need to use the solution to the quadratic equation for that. And that is, to do that, I like to put it into standard quadratic equation form. At squared plus bt plus c equals 0. And I like to move things around so that my a is a positive number. The fewer negative signs that I have floating around, the less likely it'll be for me to make a mistake. So what I typically like to do is, since I've got a negative 4.9 here, t squared, I like to bring that over to the other side. So bringing everything over to the other side, negative 4.9 becomes positive 4.9 meters per second squared t squared. Positive 10 becomes on the other side negative 10 times t, and a positive 1.5 becomes negative 1.5 once we bring it to the other side. So what we have is 4.90 meters per second squared t squared minus 10 meters per second t minus 1.50 meters equals 0. And there I've got it into standard quadratic form. At squared plus bt plus c equals 0. Now, what's the solution to the quadratic equation? You've got to remember this. This is not something, in my class, this is not something I would give you on an exam or something like that. You really need to remember this. It's a very, very common equation that pops up a lot. What's the solution? Remember, t equals negative b plus or minus square root b squared minus 4ac, and that whole thing over 2a. So, what do we have? Negative b, negative 10 is positive 10, plus or minus square root b squared, so negative 10 squared, minus 4a, the coefficient of the t squared, which is 4.9. Don't think of this as the acceleration, it's just the coefficient in the quadratic, times 4.9 times 4ac, c is negative 1.5, there we go, all over 2a, or 2 times 4.9 meters per second squared. Notice we've got a minus and a minus here, so that becomes positive. And we have a negative 10 squared, that's a negative times a negative, so that becomes positive. There we go. So we can work all that through. Now, I'm going to do this. You might have a calculator that will actually solve the quadratic for you. You might do that if you're on an exam or something like that, but I like to do this out because it actually gives us a little bit more information, and we'll talk about that in a second. I'm going to break this solution down into two parts. First, I'm going to take the 10 over the denominator, solve that, and that gives me 1.02 seconds. You can look at the units all cancel out, leaving us with seconds. Then, plus or minus, and then I'm going to take the square root part over the denominator. And that leaves me with 1.16 seconds. So my final solution is then, or my solution so far, is 1.02 seconds plus or minus 1.16 seconds. Now I'll come back to that in just a minute. So let's do the subtraction. The subtraction gives us a negative 0.14 seconds. The positive gives us a 2.18 seconds. Now first, which of these solutions do we want? Do we want the negative one or the positive one? Well, we want the positive one. So we want the 2.18 seconds. Put the 2.18 seconds into our third equation for x. X equals x naught plus v naught xt plus 1/2 a sub xt squared. We know x naught is 0. We know a sub x is 0. So this whole term is 0. 0 times anything is 0. So that whole thing is 0. That term is 0. All we have is v naught x times t. V naught x is 17.3 meters per second. times our t of 2.18 seconds gives us a final answer of x is 37.7 meters. And that is the answer we're looking for. Excellent. But let's back up just for a second. I want to look at these solutions for t here. What is this actually telling us? First of all, why do we have a positive and a negative answer? We know we want the positive one, that's our physical solution. But why do we have a negative also? Well, like from the previous problem, we know a negative time is a time before the ball was actually thrown, before the t equals 0 time, assuming that the motion continued with a uniformly accelerated motion. Let's draw this motion backwards a little bit. So we'll draw this curve back. That time would be the time back here where it passed the y equals 0 height. But notice, because of the motion still going up initially, the time before it was thrown is shorter than the time after it was thrown to make it to y equals 0. That's why our positive time is longer than the shorter negative time, because we're closer to this position initially than we are to this position. So we get a small negative time, a larger positive time. That makes sense. You ought to be able to look at those answers and make sure that it matches what you know about the problem. That's another way of checking your solution to see whether you made a mistake or not. If that weren't true, we would know that something had gone wrong. We must have made a mistake. Let's move back a step. What about this? What does this tell us? This is telling us that our time for the conditions that y equals 0 are 1.02 seconds, and then 1.16 seconds before that time, and 1.16 seconds after that time. Well, what is 1.02 seconds? What is that telling us? That's actually telling us the time that it takes to get to the peak of the motion, right there. It takes 1.02 seconds after it's thrown to get up to the highest point. And then the conditions that y equals 0 are symmetric about that point. 1.16 seconds after that point, or 1.16 seconds before that point. So this time here tells us how long it takes to get to the peak of the motion, and then the 1.16 seconds tells us how much more it takes to get to the ground, or how much time before that it would have been on the ground, assuming uniform accelerated motion. Excellent. So that really gives us a lot more information than we were looking for this problem, but it's a good thing to keep in mind so that you could always use that at some point if you needed to for a different problem. Well, there we go. There's our answer, 37.7 meters. Excellent. Let's take a look at another one. Here we go. So what's the next problem? Dr. Strange flies an airplane with a speed of 97.5 meters per second while climbing upward at an angle of 50 degrees with respect to WRT, that just means with respect to the horizontal. When the plane's altitude is 732 meters, she releases a package. Determine the velocity vector of the package just before impact, in other words, just before it hits the ground. First of all, just let me tell you, Dr. Strange, she is a friend of mine. She is a chemistry professor. This is not the Dr. Strange from the movies or anything like that. Dr. Strange is actually a real person, and she teaches organic chemistry, and she's a very good friend of mine, so I love having her in my problems here. All right, so Dr. Strange is flying this plane and puts a package out, releases a package. One thing to keep in mind is that the package is not thrown from the plane, but just released from the plane, meaning the initial velocity of the package will be the same as the initial velocity of the plane. What's it going to do? Let's draw a diagram. Well, I've already started that. So we've got our plane initially moving at 97.5 meters per second at an angle of 50 degrees above the horizontal at a height of 732 meters. The package is released. What's it going to do? Its initial velocity is going to be upward, the same as the initial velocity of the plane. It's going to come over and come down, hitting the ground. And what do we want? We want the velocity vector just before impact, just before it hits the ground. Okay, excellent. We've got our diagram. We're going to write down our variables. Let's write those down. Remember, let's say them all together. What are they? Okay, I hope you're saying them. X naught x, v naught x, vx, ax. Y naught y, v naught y, vy, ay, and t. There we go. Now, where do we want to put our origin? Well, let's talk about that just for a second again. I always typically like to put it, well, let me explain. What I like to do is put it at the lowest point in the problem and the leftmost point in the problem. So if I put it at the same height as the lowest point in the problem, then all values of y will be 0 or positive. If I put it at the most left point of the problem, then all values of x will be 0 or positive. Avoiding negative values for any of my coordinates just makes it a little bit easier for me. Like I said, the fewer negative signs I have to worry about, the easier it is. But you could put the initial, put the origin up here, and then what? Your final value for y would be negative, but that's okay, you could do that. Your y naught would be 0, but your y would be negative because it would be below the x-axis. You can do that if you want. I will typically do it this way, and I'll just be consistent. So if you always do it that way, there are certain things you can just kind of expect. So I will choose our origin over here. I'll choose my origin directly below the initial position of the plane, of the package really, and then at ground level. There we go. So what do we know? What are our variables? Well, again, x naught. What is x naught? X naught is 0. What is y naught? Well, y naught, the initial height of the package, 732 meters. X, what's x? X is the final x position. Again, we don't know what that is. What's y? Well, we know the final height is when the package hits the ground, so we know y is 0. V naught x, v naught y. So again, we need to find the components of our initial velocity. So what are those? Well, let's draw that out. We have our initial velocity has a magnitude of 97.5 meters per second at an angle of 50 degrees. V naught x will be this side. V naught y will be this side. So what are those? Well, V naught x, again, is the adjacent side to the angle. So V naught x will be the hypotenuse, the magnitude, 97.5 meters per second, cosine 50 degrees, while V naught y, that's the side opposite the 50 degrees. So what's that going to be? 97.5 meters per second, sine 50 degrees. There we go. So there is V naught x, V naught y. Multiplying those out, and what do we get? We get that V naught x is 62.7 meters per second, and V naught y is 74.5. Whoops, sorry, 74.7. Sorry, my apologies. 74.7 meters per second. Good. Now, Vx, Vy, the final components of the velocity, what are those? Well, we're not sure, so we'll leave those blank for the moment. But wait a minute, do we really not know? Well, maybe you could think ahead. We know that we know that Ax is going to be 0. So what's Vx? Think about it. What's Vx? It's the same as V naught x. So we know it is 62.7 meters per second. Excellent. Well, that's already part of the problem. We have found the x component of the final velocity. That's part of what we're looking for. Vy, we don't know that. Ay, well, we know that, again, because we defined y as positive upward. Ay will be negative 9.80 meters per second squared. And then t, do we know t? No, we don't know that. Okay, again, what are we looking for? determine the velocity vector of the package just before impact. So we're looking for the final velocity, which means we need v sub x and v sub y. Well, we have v sub x, so what else do we need? We need v sub y. So how are we going to solve that? Well, again, go to the equations. I'll give you a minute to do that. Look at the equations, see if there's any equation that has a v sub y in it, and where you know everything else. Okay, go ahead, do that. All right, I hope you've done that. What did you find? Well, I hope you noticed that we can use the fourth equation in the y motion. We don't have to solve for t. We can go directly to the fourth equation. It's got a v sub y in it, and we know everything else. We can use that to solve for v sub y. Excellent. Let's do that and see what we get. So using the fourth equation from the y motion, we have v sub y squared equals v naught y squared plus 2ay times y minus y naught. Putting in our values, we know v naught y is 74.7 meters per second squared plus 2 times ay, negative 9.80 meters per second squared. Y is 0 and y naught is 732 meters. We've got a negative times a negative, so 0 minus this is just negative 732. So we have a negative times a negative makes it positive. Square this, add that, and we end up with 1.99 times 10 to the fourth meters squared per second squared, taking the square root, and we end up with v sub y is plus or minus 141 meters per second. Now, do we want the positive or the negative root? Well, let's think about that. We've got the package coming down when it hits the ground. So what's v sub y? We know v sub y has to be negative. It's coming downward, so we want the negative root, not the positive root. There we go. What does the positive root mean? Does it have any physical meaning in this case? Well, yeah, going back the other way again, tracing this backward, we know that over here, if we were to trace this curve back, that package would actually be moving upward with a positive v sub y. So physically, that is a solution to our equations. Well, mathematically, I should say, it is a solution to the equations, but physically, it's not the solution we want. So in this case, we want v sub y is negative 141 meters per second. So we've got v sub x, we've got v sub y. Let's put them together to find the velocity vector. What do we have? We have a positive component of 62.7 meters per second in x. We have a negative component of 141 meters per second in y. There's our final velocity vector pointing down at an angle like that. So that's what we're looking for. What is the magnitude? Well, we can use Pythagoras to find the magnitude of v. We know v squared is this squared plus that squared, or v is the square root of 62.7 squared plus 141 squared. Multiply that out and we get v is 154 meters per second. Now what's the direction? Well, if we could find this angle theta, that would tell us the angle below the horizon of our final velocity vector. Well, using tangent of theta is opposite over adjacent. We've got tan theta is 141 meters per second over 62.7 meters per second. Divide that out, take the inverse tan, and we've got that theta is 66.0 degrees, which leaves us with a final result. Our final velocity vector is 154 meters per second at an angle of 66.0 degrees below the horizontal. And there we go. There is our final answer for that one. Excellent. Well, we're going to spend one more lecture looking at some two-dimensional kinematics problems. These are a little bit tricky, making sure that we read through the problem and draw the diagram. We put as much information on the diagram as we can from the statement of the problem. We choose our coordinate system. Where do we want to put the origin and what's the orientation of our coordinates? What are the values for, then we write down the variables. What are the values for all of those variables? And then how do we go about finding what are we looking for? When we're writing the variables down, what do we know? What do we not know? And what are we looking for? And then how do we find those values of what we're looking for? All right, great. Well, we'll do that again next time. I hope you enjoyed it. I'll see you then.